All right, this last little part is about really finding the equivalence points, finding the pKa of something if you don't know what the acid is. So we are going to do a lab with this. And you can identify an acid based on its titration curve. Okay? Because what we can do from the titration curve is find the pKa. So I am going to show you how to do that. Essentially, what you're going to do, and the computer will do this for you, so if you haven't had calculus, don't worry. You're going to take the derivative. Take the derivative to find the exact inflection point or equivalence point. Equivalence point. Okay. Because at the equivalence point, this is what is considered the half. Oh, sorry. Not the half. The equivalence point is when everything is neutralized, right? Inflection point is completely neutralized. Now, why do we care about that? Well, if you can figure that out, where it was completely neutralized, you can find half of that. That's where the money is, all right? I'm looking at this. Say I took the derivative. I found the exact equivalence point. Okay, it took 15 milliliters to get to the equivalence point. I can find that from this graph, okay? Now, what's half of 15? 7.5. So this is called the halfway to the equivalence point. Why is this point significant? Well, when we are halfway to the equivalence point, that means that half of the HA has turned into A minus. Now, if half of it has been converted, that means that I have the exact same amount of HA and A minus. So at the half equivalence point, HA equals A minus. Okay, now I want you to think back to the Henderson-Hasselbalch equation. pH equals pKa plus the log of A minus over HA. If this equals 1, then this whole part is 0, and that is where the pH equals the pKa. So at the halfway to the equivalence point, pH equals pKa. That's why this point is significant. All right, so this is why we care. Okay, because you can identify an acid if you know what its Ka value or you know what its pKa value is. All right, so that is going to be important in the lab. Again, the computer will find the derivative for you. Now, what if it's a polyprotic acid? It technically has 2 equivalence points. So you could find the Ka1 and the Ka2. So I would look for my first inflection point, and halfway to there, so about right here, would be my pKa1. And then between the two, about halfway to there, would be my pKa2. So it's actually going to have 2 equivalence points and 2 inflection points if it has 2 acids. Okay, so for polyprotic, you have multiple inflection points or equivalence points, 1 for each hydrogen. Okay, you do need to make sure you measure from one point to another to find the pKa. What I mean by that is my pKa2 is halfway between 1 and 2. It's not halfway from the beginning to that next point. All right, so kind of keep that in mind. That's where we're going to find those. Another thing you can notice about titration curves is how they change with different Ka. So the weaker the acid, the higher the pH is at the equivalence point, and the higher it starts. You can just kind of notice those things. So a weak acid, higher equivalence point pH. Okay, these are all things that should kind of be clicking into place. If I do a titration curve for a weak acid, I can notice these things. All right. We are going to do one calculation here. It says, what is the pH at the equivalence points made by adding 25 milliliters of 1 molar? Whatever this acid is, we don't even know, but we know it's got to be a weak acid because it starts with hydrogen. 25 milliliters of 0.1 molar sodium hydroxide. And I gave you the Ka. this is really a titration calculation that I did before, so you should be able to do this. How do I calculate the pH at the equivalence point? 2 steps. 1, figure out how much A minus there is. Well, if it's at the equivalence point, all of this has been converted into the A minus or C6H4NO2 minus. And then I can use, can't use a Henderson-Hasselbalch because all of it has been converted. So you are going to have to use an ice table with that A minus. So go ahead and set that up and give it a try. Okay, so you should have gotten 8.78. Essentially, I knew all of the acid had been converted, so that is 0.0025 moles. Now, this is an ice table, so I did have to put it over the total milliliters or liters, essentially. Since I had 25 and 25, so it's 0.05. So then I did minus x plus x plus x, solved. Now, I did use Kb because this is a Kb equation, right? A minus is a conjugate base, acts like a base, you need a Kb. So I did 1 times 10 to the negative 14th over 1.4 times 10 to the negative 5th. Drop my x as per usual. X is 5.98 times 10 to the negative 6. Plug that in, find POH to find the pH. Does my answer make sense? Well, yes, this is a weak acid. So at the equivalence point, the pH should be a little bit basic. Okay. Now, last thing I want to talk about for these titrations is different indicators. Now, we almost always use phenolphthalein. You'll notice we do like an iodine one. We can use all kinds. There's a couple reasons that phenolphthalein is used for almost all titrations, and I'll talk about that in a sec. But essentially, all of these color changes could be used for different acid-base titrations. Okay, so how do we choose which one is best? And why do we use phenolphthalein, this guy, most of the time? Okay, so essentially you want to choose based on when the pH equilibrium or equivalence point occurs. Okay, the important thing is we want it to change, after the equivalence point, because of that whole inflection thing of inflection. All right, so if we think about it, we want it to change after the point because there's such an inflection there. If you go a little bit past, that's totally fine. Though if you go a little bit before and we're doing a weak acid and a strong base titration, which is what we're usually doing, that's actually going to throw off where your equivalence point is. So phenolphthalein, you'll notice, doesn't change until over here, okay? Pretty high pH, but essentially we want something after 7 to change. Also, phenolphthalein goes from clear to pink, which is a very easy to notice change, okay? So we want it to change after the inflection point, and we prefer a drastic color change. Okay, not like a spectrum. So if you got one that changes from green to blue, where's the inflection point? How green is it? Okay, that's kind of hard to tell. So phenolphthalein changes drastically, and it changes after most of our inflection points, which is why we use it a lot of the time. Okay, you can kind of see that on this graph. Okay, phenolphthalein is going to change up here, essentially. Methyl red, however, which would change right here, and that's one we have pretty readily available. That's actually really going to throw off our Ka. Okay, if you look at where the equivalence points are for strong acid and weak acid, phenolphthalein is after both of those, but this is such a strong inflection point, it could happen anywhere in this milliliters. It really wouldn't change our thing. However, because this is like a straight up and down line, if it was between methyl red, it could be anywhere from here to here, or here to here, essentially. And that's a big difference in milliliters, which really affect our pKa. So we want to use phenolphthalein because it changes closer to the inflection point for both. Changes closer to inflection. Oops, and I left out a lot of letters. Point for both of these acids. Okay, methyl, bad. Methyl would change closer to the midpoint instead of the inflection points. And it would require you to be a lot more specific for your weak acids. Okay, so phenolphthalein just makes it a heck of a lot easier. You want something that changes after because that's where you're going to have a nice, great spike. And you want a drastic color change. So that's kind of how we choose our indicators.